NASA confirmed Thursday that the Voyager 1 probe would make history by becoming the first human-made object.
Something strange just happened at the edge of our solar system. Voyager 1, the farthest human-made object in space, has encountered an event that no one can explain. An energy burst, a mysterious force, and a signal that doesn't match anything we've ever seen before. Is it a glitch, a natural phenomenon, or something else entirely? After nearly 50 years of silent travel, Voyager may have stumbled into the unknown. What did it find out there billions of miles from Earth?
Its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again. The spaceship left the solar system in 2012 and is currently more than 15 billion miles from Earth.
Voyager 1, launched on September 5, 1977 from Cape Canaveral, was initially part of a mission to explore the outer planets. It was built with a primary goal of studying Jupiter and Saturn, sending back data that would reshape our understanding of the outer solar system. The spacecraft provided humanity with its first close-up images of these distant worlds and their moons, rings, and magnetic fields. At the time, its mission was ambitious but finite, expected to last just a few years. Nearly 5 decades later, Voyager 1 continues to operate, having traveled more than 15 billion miles from Earth. It is now the most distant human-made object ever created. While it no longer serves its original purpose, it has transitioned into a new phase of exploration. Its current mission is to study the interstellar medium, the space between the stars, which remains one of the least understood regions in astronomy. Crossing the helipause, the boundary where the solar wind slows down and merges with the interstellar wind, was a key moment. It was not marked by fireworks or grand public announcements at the time, but within scientific circles, it was a huge event. Voyager 1 became the first human-made object to leave the protective bubble of our solar system and enter the vast expanse of space that lies between stars. Despite the enormous distance, the spacecraft still communicates with NASA's Deep Space Network. Its power source, a radioisotope thermoelectric generator using plutonium-288, is still active, although gradually weakening over time. Voyager 1 sends back data using a 20-watt signal, roughly equivalent to a refrigerator light bulb, which takes more than 22 hours to reach Earth. And now for This Week with Matt, about the signs of nature, which are greater than we think, but they're not on top of, and all the tools of our trade are unloaded. So, post the fact that such a signal can still be received and interpreted across this distance is a technical achievement in itself. The instruments still functioning on board include the magnetometer, plasma wave instrument, and cosmic ray detector. These tools help monitor changes in the environment around the spacecraft. After crossing into interstellar space, scientists expected the data to show a gradual shift. Lower levels of solar particles, a slight change in magnetic fields, and a steady increase in galactic cosmic rays. And for many years, that's exactly what they observed. The region Voyager 1 has entered is not just empty, it's incredibly quiet. Scientists describe it as the most peaceful environment known in the universe. There are no planets, no nearby stars, and no solar storms or radiation spikes caused by the sun. The spacecraft is now traveling through a near-perfect vacuum, where particles are few and far between, and where any detectable event is rare. This quietness was actually one of the reasons why researchers could be so confident that Voyager had passed into interstellar space. Inside the heliosphere, the sun's influence dominates particle behavior. Outside of it, these patterns change. Data from Voyager's plasma wave instrument showed an increase in the frequency of plasma oscillations, which scientists interpreted as a sign of denser interstellar plasma, confirming the crossing. But plasma incination doesn't come on wide twice. The crossing itself occurred in 2012, although NASA took time to verify and analyze the data before making the official announcement in 2013. Researchers were cautious, as it wasn't immediately clear whether the data indicated a true boundary crossing or just an area of fluctuating solar influence. Eventually, multiple data sets confirmed the conclusion. Since then, Voyager 1 has continued its journey, moving deeper into interstellar space. Its course is not directed by any propulsion system. It relies on the momentum it gained from its planetary flybys in the 1970s. The path it follows is straight and uninterrupted, influenced only by gravity and the extremely faint drag of interstellar particles. From a technical perspective, what makes this even more impressive is the fact that the spacecraft is operating on technology from the 1970s. Its memory capacity is tiny by today's standards, about 68 kilobytes in total, and it uses an 8-track digital tape recorder. Engineers on Earth must send commands in advance, and due to the distance, it takes almost a full day to receive a response. Although many of its subsystems have aged well, NASA engineers face increasing challenges in maintaining communication and interpreting the data it sends. With limited power and no chance of repair, each year of continued operation is seen as a gift. Yet despite these limitations, Voyager 1 remains a functioning scientific tool, and its presence in interstellar space provides a unique opportunity to study a region that no other probe has reached. Voyager 1's long lifespan is not just a matter of luck. Its systems were built with redundancy and resilience in mind. It was designed to operate far from Earth without real-time support. Its software has been updated several times over the decades, sometimes by rewriting instructions and uploading patches to accommodate shifting goals or fix minor issues. Engineers also regularly switch between instruments to conserve power and prioritize key data collection. The scientific value of Voyager 1 lies not just in what it finds, but in what it continues to rule out. Its data helps confirm existing models of space physics and occasionally challenges assumptions about how our solar system interacts with the interstellar environment. For example, measurements of cosmic ray intensity from the probe have helped refine our understanding of how high-energy particles behave beyond the sun's influence. Despite the vastness and emptiness of the region it is in, Voyager 1 still has more to tell us. Scientists are particularly interested in how the interstellar medium changes as the probe moves further from the sun. They expect to observe variations in particle density, magnetic field strength, and cosmic ray levels over time. These measurements are essential for building a more complete picture of the galaxy's structure and behavior. Voyager 1 represents more than just a spacecraft. It symbolizes human curiosity and the drive to explore the unknown. It carries with it the golden record, a time capsule of Earth's culture, languages, music, and greetings intended for any intelligent life that might one day encounter it. While the chances of that happening are slim, the message is clear. Humanity has ventured into deep space not just with instruments, but with intention. For many years after crossing into interstellar space, Voyager 1 continued its journey in relative silence. The spacecraft, traveling over 15 billion miles from Earth, maintained a steady rhythm of data transmission. Its instruments continued to record background noise from the interstellar medium, low-level plasma waves, cosmic rays, and faint magnetic fields that told a quiet story of the environment between stars. Scientists expected this routine to continue indefinitely, or at least until the spacecraft's power supply eventually failed. But then something changed. In late 2023, NASA engineers noticed a disturbance in the data stream. At first, it seemed minor, just a small irregularity in the telemetry. This wasn't unusual considering Voyager 1's age and the extreme conditions it has endured. The spacecraft had already surpassed all expectations, and minor glitches in signal or performance were considered normal. However, as the team reviewed the data more closely, it became clear this wasn't a simple hardware hiccup. The signal irregularities were consistent across multiple instruments. The spacecraft's magnetometer, plasma wave sensor, and cosmic ray detector all picked up a distinct anomaly, an unexpected burst of energy that lasted only a brief moment but left a strong imprint in the data. The pattern wasn't random. It showed structure, timing, and coordination that immediately raised questions. Every major sensor recorded the same spike down to the millisecond, and the signal had a clear beginning and end. Engineers at NASA's Jet Propulsion Laboratory began a full system diagnostic. They checked for corrupted memory banks, degraded systems, or potential issues caused by radiation exposure. Given Voyager's age, any number of onboard failures could explain unusual readings, but the results were surprising. Every onboard system passed its checks. The spacecraft was healthy, memory was intact, the power systems were stable. The problem wasn't coming from Voyager itself. As the analysis deepened, the team ruled out internal errors. The anomaly hadn't originated from within the spacecraft. It had come from outside, an event that appeared to have interacted with the entire spacecraft simultaneously. This realization prompted a new phase of investigation. Scientists turned to external factors: solar activity, cosmic radiation, micrometeoroid strikes, and any known cosmic events that might line up with Voyager's current position. None of the usual suspects matched the signature. There had been no solar flares or coronal mass ejections from the sun capable of reaching that far. No gamma-ray bursts or pulsar signals had been reported in that sector of space. No gravitational waves had been recorded by ground-based observatories that might explain the disturbance. The data from Voyager stood alone, an isolated, unexplained event in one of the quietest regions of the known universe. What made the situation more intriguing was the nature of the energy burst. Unlike most space phenomena, which are typically chaotic or noisy in terms of frequency and amplitude, this event exhibited a smooth and structured waveform. Scientists likened it to a pulse, short, focused, and highly coordinated. The energy passed through every sensor aboard Voyager 1 in a perfectly timed sequence. Nothing in the data appeared accidental or haphazard. Adding to the mystery was the fact that the anomaly left no damage. None of Voyager's systems were compromised. The data resumed its normal rhythm immediately after the event. There was no sign of interference or malfunction. It was as though something had passed over or through the spacecraft, touched it momentarily, and moved on. This kind of event had never been seen before by any spacecraft, especially one so far from home. The Deep Space Network, which handles communication with Voyager, recorded this signal in real time and preserved every bit of data. Multiple teams, both inside NASA and in external research institutions, were brought in to analyze the event. The working assumption was that if this had been a natural occurrence, it would have a precedent, or at least a similar counterpart elsewhere in space data archives. But no comparable signals could be found. This wasn't like cosmic background radiation or plasma oscillations caused by solar activity. It wasn't interference from Earth, and it wasn't a telemetry decoding issue. It was something else entirely, an event that didn't fit into any known category of space science. The magnetic field readings during the event showed a rapid but highly localized shift. The plasma wave instrument detected a sudden rise in electron density, but only for a fraction of a second. The cosmic ray detector recorded a narrow band spike, again brief and sharply defined. Together, these findings painted a picture of a concentrated external force, a brief, directed burst of energy from an unknown source. And while Voyager 1 had encountered solar wind, radiation spikes, and magnetic field changes before, none had appeared like this. The consistency across all instruments suggested that the probe had passed through something coherent, something with structure, yet nothing in current astrophysical theory predicted such an event occurring in deep interstellar space. In response, NASA escalated the anomaly investigation. Internal communications grew urgent. While there was no risk to the spacecraft itself, the implications were significant. If an unexplained force or energy pattern could act on a spacecraft in interstellar space, then our understanding of that region was incomplete. Engineers and physicists began developing new hypotheses ranging from interactions with unknown particle fields to potential contact with phenomena we don't yet have a framework to describe. Some researchers proposed that Voyager might have crossed a boundary within the interstellar medium, a region where magnetic fields or cosmic particles behave in unexpected ways. Others speculated about interactions with exotic forms of matter, such as dark plasma or undetected filament structures, but with only one data point and no visual confirmation, all theories remained speculative. Complicating matters further was the scale involved. Voyager 1 is moving at over 17 kilometers per second. Even a short-lived event encountered at that speed would have involved interaction with millions of kilometers of space. Yet the signal was incredibly precise, lasting only milliseconds. It would take more than theory to explain how something so brief and sharply defined could emerge in a region considered to be largely uniform and uneventful. The event also reignited discussions about the limits of current instrumentation. Voyager systems were never designed to detect or interpret anomalies of this kind. The spacecraft sensors are relatively basic by today's standards. The fact that they still managed to record such a precise event raises questions about what else might be occurring undetected in deep space. As the data was shared with other observatories and space agencies, a consensus began to form. The anomaly was real, it was external, and it was unlike anything previously recorded. The scientific value of the signal is now considered immense. Even if it cannot be fully explained with current technology or theory, it offers a rare glimpse into a part of the universe that is still largely unknown. In the days following the detection of the anomaly, NASA's Voyager 1 team remained focused on verifying the integrity of the spacecraft systems. On the surface, everything seemed fine. The instruments were operational, the power output was stable, and the data transmission had returned to normal. However, further investigation revealed something even more puzzling: evidence that Voyager 1 had physically moved. This was not just a drift or gradual shift that might be expected from an aging spacecraft. The data suggested a sudden, measurable change in orientation. Voyager's onboard gyroscopes, which help monitor the probe's orientation in space, showed a brief but clear rotational movement. In other words, the spacecraft had experienced a twisting force that changed the direction it was pointing. This discovery triggered another round of detailed system checks. The first question was whether this movement had been caused by Voyager's own attitude control systems. These include thrusters and reaction wheels that were originally designed to keep the spacecraft's high-gain antenna aligned with Earth. Over the years, these systems have been used very sparingly, mostly for minor adjustments. The engineers checked the logs and fuel levels to see whether any such systems had been activated. The answer was no. There had been no thruster firings. The fuel reserves were unchanged. The reaction wheels, which were designed to provide gentle rotation, had not moved. There were no commands sent from Earth that could have triggered an adjustment. This ruled out internal controls as the cause of the motion. That left only one other possibility: an external force. But what kind? In deep space, there are only a few known influences that can exert a force on a spacecraft. One is solar radiation pressure, the gentle push of sunlight on a spacecraft's surface. However, Voyager is now well beyond the point where solar radiation has any significant impact. Another possibility is a collision with a micrometeoroid or interstellar dust particle. Even something tiny traveling at high speeds could, in theory, impart enough force to cause a minor change in orientation. To test this idea, engineers reviewed data from the spacecraft's external sensors. Voyager 1 is equipped with instruments capable of detecting impacts and radiation. These sensors showed no sign of any collision or disturbance. No sudden vibration was recorded and no high-speed particle impact was logged. The thermal sensors also remained stable, indicating there was no sudden heating or mechanical shift due to debris or friction. If something had hit the spacecraft, there should have been at least some evidence, but there was none. The team also examined environmental data. Was there any burst of plasma, magnetic fluctuation, or high-energy radiation that might have affected the spacecraft? Again, the data showed nothing consistent with a natural external push. The space around Voyager 1 appeared calm and no other cosmic event was recorded at that location. Still, the gyroscopes told a different story. The measurements were unambiguous. A short directional force had acted on the spacecraft. The rotation was subtle, but in the context of spaceflight, even the smallest change can become significant over time. Given Voyager's immense distance from Earth, a shift of just a few microradians could cause its antenna to drift off target, affecting communication. This discovery added a new layer to the earlier energy burst. First, there was a complex structured signal that passed through the spacecraft systems. Then, shortly after, there was a small but precise physical motion, an unexplained push. The alignment of these two events was too close to ignore. While the energy burst had left no lasting disturbance in the data systems, the physical nudge had created a real-world effect that was measurable and verifiable. As part of their investigation, NASA's engineers simulated various scenarios using Voyager's flight software. They modeled the effect of minor internal faults, spontaneous memory errors, and mechanical shifts caused by long-term wear and tear. None of the simulated cases matched what had occurred. There was no recorded malfunction, no random behavior, and no sign of stress in the spacecraft's frame. The movement was smooth, clean, and temper, more like a calculated maneuver than a mechanical fault. To further validate their findings, the team reviewed historic data going back decades. In all of Voyager 1's mission history, no similar event had occurred. The spacecraft had always responded predictably to commands, and its attitude had remained steady over long periods. This incident was a clear deviation from that pattern. Another important factor was the direction of the movement. The spacecraft's shift was not random. It followed a specific vector, a direction in space that aligned with the same orientation from which the earlier energy anomaly had arrived. This reinforced the idea that the two events were connected. First came the energy burst, then came the motion, both originating from the same spatial direction. Given the extremely low probability of this occurring by coincidence, the team began to consider whether Voyager had passed through a region of space unlike any encountered before. Could there be a type of localized field or force that acts on objects in a very narrow range? And if so, why had no other spacecraft detected it? One explanation lies in Voyager's unique position. It is the only operational probe located in interstellar space at such a great distance from Earth. Other spacecraft, like New Horizons, are still within the Sun's heliosphere. That makes Voyager 1 the only real sensor we have in that environment. Its observations cannot be confirmed by any other platform, and no mission currently planned will reach a similar position for decades. The movement also raised concerns about the long-term orientation of the probe. If Voyager had been nudged off course even slightly, it could eventually affect its ability to maintain communication. The high-gain antenna must remain precisely pointed toward Earth to transmit its weak signal. A minor misalignment now could become a critical problem years later, especially as the onboard power continues to decline. In response, engineers used the Deep Space Network to track the spacecraft's signal strength and orientation. They confirmed that the antenna was still within the acceptable range, the movement had occurred, but it hadn't disrupted communication. Voyager was still operational, still sending data, and still on its general path. However, the event highlighted the fragility of the mission at this stage. With no propulsion capability and no physical way to adjust course, any future disturbances could prove more serious. The fact that this external force, whatever it was, left no lasting damage adds to the complexity. It wasn't violent, it wasn't sustained, and it didn't appear to affect Voyager's systems beyond the brief shift in orientation. In effect, it behaved more like a tap than a shove. But even that subtle interaction challenged the assumption that the interstellar environment is completely passive. For years, space beyond the solar system has been thought of as largely empty, containing a thin mix of particles, weak magnetic fields, and scattered cosmic rays. Events there are expected to unfold slowly and predictably. But this incident suggests that the region might hold surprises. There could be features or forces that we haven't yet observed or understood. The findings were both precise and unexpected. Voyager 1, at the time of the event, had entered a spatial coordinate that had been theorized but never before observed directly, a kind of node in interstellar space where galactic magnetic fields intersect and effectively cancel each other out. This node, sometimes referred to in academic literature as a magnetic null point, had long been a mathematical concept rather than a verified location. In theory, such a point represents a rare balance, a location in space where magnetic pressures from different directions even out completely. Unlike the broader voids between stars, which are characterized by low particle density, this specific region was defined by the interaction, or rather the cancellation, of background magnetic fields. Until Voyager 1 passed through this exact point, there had been no way to detect or confirm such a place existed. The significance of this alignment was not lost on the scientists. Voyager's instruments recorded a moment of profound stillness. The usual background fluctuations in plasma, cosmic rays, and magnetic field strength dipped sharply just before the energy burst occurred. In the moments leading up to the anomaly, space around the spacecraft appeared unusually calm, even for interstellar standards. This calm was followed by the structured energy event and the subtle torque that briefly shifted the probe's orientation. The probability of Voyager 1 passing through such a unique location by pure chance was statistically negligible. In astrophysical terms, it was an improbable alignment, almost impossible to plan or replicate. The spacecraft had not only entered an area of theoretical interest, but had done so at precisely the moment an unexplained event occurred. This raised fundamental questions about the nature of the event itself and whether it was related to the node's unusual properties. One of the most puzzling discoveries came from the analysis of the energy burst's waveform. Initial observations had already noted its structured form and narrow frequency range, but further analysis revealed something far more complex. The signal was composed of multiple overlapping frequencies arranged in what looked like a harmonic pattern. It was not simply a burst of raw energy. It appeared to be layered, organized in a way that resembled a signal or field designed with intent. To be clear, no one at NASA or in the wider scientific community has claimed that the signal was artificial or a form of communication. The language used in the internal reports remained cautious. However, the structured nature of the waveform was unlike anything produced by known astrophysical processes. It didn't resemble random cosmic radiation, nor did it behave like the electromagnetic emissions from stars, pulsars, or black hole events. This unexpected complexity led to even more urgent data reviews. Scientists tried to cross-searching the signal with every known type of astrophysical burst: gamma-ray bursts, magnetar flares, and even the microwave background noise left over from the Big Bang. None matched. The signal didn't fit into any known category. It stood alone as a new type of event, unclassified, unexplained, and, for the moment, unrepeatable. At NASA's Jet Propulsion Laboratory, internal discussions turned toward long-term implications. If this signal had not come from a known cosmic process, what was its origin? Could it be the result of a natural phenomenon that had never been encountered before? Perhaps a previously unmeasured interaction between interstellar plasma and magnetic fields? Or had Voyager 1 stumbled across a type of galactic feature that defied current scientific models entirely? The conversation also took on a more philosophical tone. For nearly 50 years, Voyager 1 had traveled outward as a passive observer, gathering data, studying particles, and quietly transmitting the story of its journey. But now something had responded. Whether intentional or not, the probe had been touched by an event that left a measurable mark. It was not just observing the universe anymore, it had become part of a story no one had anticipated. Within NASA, the event prompted the classification of an internal report. While details of the energy signature and spacecraft movement were made available to collaborating scientists, the full context of the analysis, including speculative interpretations and future risk assessments, was not released to the public. Internal sources later revealed that the anomaly had triggered an unusually high level of concern, not because the spacecraft was damaged, but because the event had no clear explanation. The concern was not about failure, but about the unknown. In science, unexplained phenomena are usually welcomed as opportunities for discovery. But in this case, the distance, the uniqueness, and the precision of the event made it difficult to approach in conventional ways. There were no control experiments, no additional spacecraft nearby to corroborate the data, and no precedent to draw upon. Voyager 1 was alone. and it had reported something no other human-made object had ever encountered. The wider scientific community began to discuss new possibilities. Was it time to revise our understanding of the interstellar environment? Could there be types of matter, energy, or interaction that current physics has not accounted for? Some researchers began modeling the idea of spatial nodes locations, where the fabric of space behaves differently, creating conditions where energy could accumulate or manifest briefly. Others explored the idea of unknown fields, hypothetical constructs that could exist alongside known forces but remain undetectable until the right conditions align. Whatever the ultimate explanation, the implications were significant. If such anomalies exist in interstellar space, then future missions will need to account for them. This includes not only physical spacecraft design, but also the way we model navigation, communication, and long-term mission planning beyond the solar system. It also raised questions about whether Voyager 2, currently following a slightly different trajectory through interstellar space, might encounter a similar phenomenon. To date, Voyager 2 has not reported anything comparable, though it continues to send back valuable data. The two spacecraft are not in close proximity, so direct comparison is limited, but NASA teams have begun paying closer attention to Voyager 2's signals just in case. For now, Voyager 1 continues its journey. The spacecraft has resumed its normal data transmission, and no new anomalies have been reported since the incident. But the data it captured during those few minutes has already had a lasting impact. Scientists are still combing through it, looking for new patterns, correlations, or insights that might help place the event in a wider context. The nature of the signal, the precise orientation of the spacecraft, the unique spatial coordinate, it all points to a moment where the predictable silence of deep space was briefly interrupted. Whether that interruption was natural or something else remains unknown. It is still moving away from Earth, still powered by its slowly dwindling plutonium source, and still sending home the faint radio pulses that began in the late 1970s. But now it carries with it not just the legacy of planetary exploration, but the mystery of something far stranger, something that appeared, interacted, and then vanished, leaving behind only questions. The anomaly, the rotation, the harmonic signal, they may never be fully explained, but they serve as a powerful reminder of just how little we truly know about the cosmos. Voyager 1 was built to explore, and it has, but now it may have done something even more important. It has hinted at a frontier beyond our current understanding, a boundary not just of distance but of knowledge itself.